Hello and welcome to our lab demonstration on measurement of length. This experiment will introduce you to the method and techniques of using high precision instruments for the measurement of length. The first instrument we will master is the vernier caliper. We have three uses of this tool. This bottom section uses the fixed and movable blade jaw to measure the outer diameter of an object. For example, I have this cylinder and I can make use of the vernier caliper using the fixed and movable jaw blades to measure the outer diameter of the cylinder. The top section also has a fixed and movable blade, which we call the knife edge, which is used to measure the inner diameter of an object. For example, we have an hollow cylinder here, and we can use this to measure the inner diameter of the cylinder. While we have the depth bar, the depth bar is to measure the depth of an object. For example, a cylinder, and I can measure the depth of this cylinder using the bar side of the vernier caliper, like this. Now that we know the uses of the vernier caliper, we need to understand a very important concept called the least count. The vernier caliper has two scales. The first scale is the fixed one, which is along this line, called the main scale. Usually it is in centimeter, or you can have it also in millimeter. So you have it on this instrument, for example, between the value of 0 to 12 centimeter. That is the main scale. And on the main scale, we have a movable scale that moves along the main scale, which is called the vernier scale. Now, we need to know the least count of this instrument. The least count represents the least or the smallest value that this vernier caliper can measure. So looking at the main scale, we can see that we have 10 scales or 10 marking between 0 and 1, which means that each line or marking is 0.1. 0.1 represents the least value that this instrument can measure. Knowing this, we can therefore determine the least count. Now that we know the smallest scale, then we need to go now to the vernier scale. The vernier scale has some markings and is just a division of the 0.1, which is the smallest value that can be taken on the main scale. For the example, this vernier caliper has 10 markings. So to take reading on the vernier scale, one has to look at the coincident number or position that align perfectly with the main scale. By the time we are taking a measurement, I'll go further on that. Now, to calculate the main scale, to calculate the vernier scale, now to calculate the least count is given as the smallest value on the main scale divided by the number of division on the vernier scale. So to do this, it means that the least count represented as LC is equals to 0.1 represented as the smallest value that can be measured on the vernier scale divided by the number of division on the vernier scale. In this case, the vernier scale has 10 division. So 0.1 centimeter divided by 10 will give us 0.01 centimeter. And that is the least count. This is what we expect you to do when you come to the lab. So this is another type of vernier caliper, and here is the main scale that runs on the longer section of the instrument, and the movable part, like I said earlier, is the vernier scale. Now you can see on this instrument we have 0.05 millimeters. So how is 0.05 obtained? So if you look at this again, the smallest division on the main scale is 0.1, okay, which is what we have here. But the number of division on this scale is not 10, rather it is 20 lines. So if you begin to count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have 20 lines. So if we divide 0.1 divided by 20, that would give us, that is 0.1 centimeter divided by 20 will give us 0.005 centimeter. 0.005 centimeter is the same as 0.05 millimeter as written on the apparatus itself. So now that we know the concept of the least count, we need to take a measurement using the apparatus. So the first thing we are going to do is to check for zero error on the apparatus. So the zero error is going to be checked by collapsing or closing the jaws of the vernier caliper and ensuring that and observing that the zero marking on the vernier caliper coincide with the zero marking on the main scale. So if the two markings are aligned, then it means that the instrument has no zero error. However, if there is any misalignment, take note of it as the offset that we'll use later on in the calculation. As you can see, this instrument has no zero error. So we can then proceed by measuring the outer diameter of this cylinder. So this is a cylinder, and if I want to measure the outer diameter of the cylinder, I'm to use the bottom section of the instrument like this by closing the fixed and movable jaw together. Then I have a screw knob here to ensure that my object to measure is held in place. Now, once I have this, the first thing I need to do is to note my main scale reading. The main scale reading is obtained by looking at the zero marking of the vernier that aligns with the main scale. Or you take the marking of the zero mark on the vernier scale that aligns on the left scale of the main scale. So we'll note down our main scale reading. So our main scale reading which we're going to call NSR is 1.1 centimeter. You may observe that the reading may exceed 1.1, but the instruction says that take the reading on the left side of the zero mark of the vernier. The next stage now is to look at all the markings on the vernier scale and find the division that coincide with that of the main scale. So we are going to get our vernier scale reading. So our vernier scale reading is going to be, so our vernier scale reading. So we are going to represent it as VSR to be the ninth position multiplied by the least count of this instrument, which is 0.05. But we are not going to use 0.05 millimeter, but rather we are going to use 0.005 centimeter for consistency of our unit. So I'm going to multiply by 0.005 centimeter, 0.045 centimeter. So our total reading or our final reading becomes the sum of our main scale reading and our vernier scale reading, giving 1.1 centimeter plus 0.045 centimeter, and this gives us 1.145 centimeter as our final score. Zero error. As you can see on the instrument with me, there is no zero error. The vernier scale and the main scale zero mark both aligned. But what if you have an instrument that has an error? In the sense that the marking on the main scale and the vernier scale, suppose that this is your main scale, and suppose that this is your main scale zero mark, and this is your zero mark on your vernier scale. So let's say this is 1, 2, 3 like that up to 9, and here this is your markings 1 like that, 2 in that order. So in this case now, you can see that the zero mark on your vernier scale and that of your main scale are not aligning, hence there is an error. And you can also have another case whereby you have a situation like this, whereby you have the zero marking. So sometimes you can also have another special case whereby you have your zero mark like this, and your zero mark is leading the zero mark of the vernier scale. So in another case, you can have a situation like this, whereby you have your vernier, the main scale zero mark is leading the zero mark on the vernier scale. Something like this. In that order. So how do you deal with these two types of cases? So the first one, whereby you have your zero mark on your vernier scale, is leading that of your zero mark of your main scale. So your final reading, you note down the zero error. So in a case whereby, so that is the vernier scale is leading. So in a case like this, you note down the error. And how do you note down the error? You still need to look at the main scale reading will be 0, depending on what you have here, because we said it's always on the left hand side. Look at the zero mark on your vernier scale, you trace it down to the main scale to get your main scale reading. Then you look at the coincidence, that is the position of division on the vernier scale that coincide with the lines on the main scale. So that is how you take your reading of your zero error. With that, then your final reading that you obtained from the addition of the main scale reading plus the vernier scale reading, then you now subtract the zero error from it. So that is what your final reading will look like. While in a case like this, where you have your main scale reading is leading, the zero mark of your main scale reading is leading the zero mark of the vernier scale. In such a case, your final reading becomes the sum of your main scale plus your vernier scale reading minus. So in this case, you are not subtracting again, but it's going to be plus your zero error. So it means that your zero error can be added or subtracted to your final reading. So next we move to another instrument that has a higher precision than the vernier caliper. This instrument can be used to measure the outer diameter of an object like this. As you can see, it allows me to measure the outer diameter. So the micrometer screw gauge can allow you to measure the outer diameter of the cylinder by closing the anvil and the spindle to the object like this. So you all need to rotate the ratchet until it claps, and since you'll be taking this measurement more than once, it's better you are consistent with your measurement by ensuring the same pressure all throughout the experiment. So the rule of thumb is, as soon as it closes up, you turn this ratchet until you get like 3 clicks, then you stop, and you can do that consistently with with other objects that you want to measure. Now that you have your object in place, you are left to take the reading on the micrometer screw gauge. Before we move on to taking the reading on the micrometer screw gauge, there are a couple of things we need to note. Number one, the main scale reading. The main scale reading is the division that is on the sleeve of the micrometer screw gauge. As you can see, these are numbers that range between 0 millimeter to 25 millimeter for this instrument. Now, it is important also to note the bottom markings, which is always called the half point marking, which is always 0.5. So if you look closely, you see on the top marking, you have 0 millimeter, 1 millimeter, 2 millimeter, like that, up to the edge of the thimble. Now, under this datum line, you have the half mark, so you have 0. Then if you consider the marking below becomes 0.5, you go to the top, you have 1 millimeter. Then if you go down, you have 1.5 millimeter, and so on. So always remember the half point markings. Now that we know how to take the reading on the main scale, we need to look at the table and look at the markings on it. For this instrument, the marking starts from 0 up to 50 because it takes a 360 markings. Although the same position where you have the 0 mark is where your 50 point is. So if you count like this, you have 0, 5, 10, up to 45, 46, 47, 48, 49, then back to 0, which makes it 50. Now, we need to look at the least count of this instrument, which we call LC. And the formula of the least count is always the smallest value or smallest division on the main scale divided by the number of divisions on the vernier scale. In the case of a micrometer screw gauge, as I've shown you on the main scale, the smallest division we can measure is going to be 0.5. So it is not 0. 0 means that you do not have anything between the anvil and the spindle. So the least we can measure here, or the smallest we can measure here, is 0.5 millimeter. So if you look at the number of divisions on the vernier scale is 50, as we identify on this instrument. So now we need to now divide 0.5 millimeter by 50 to get our least count. So our least count is going to be 0.01 millimeter. And this is usually written on the instrument itself. Now that we know the least count, we can get our measurement of the outer diameter of this cylinder. The first thing we need to do is to close the micrometer screw gauge to get the zero error on the instrument. We want to note the line on the datum line, which is the horizontal line on the main scale, that coincides with the line on the vernier scale. On this instrument, once I close it, three times on the ratchet, that is 3 clicks on the ratchet, you can see that this instrument has a zero error. And the zero error can be obtained by looking at the datum line that coincides with the vernier scale. So if we take our readings here, we have 25, 26, 27, 28. So it means that the position we have on our vernier scale, so our zero error, is going to be 0 for the main scale plus 25, which is the position on the vernier scale, multiplied by the least count, which is 0.01 millimeter. So this will give us 0.25 millimeter. So later on, we are going to subtract this error from our final reading. Now let's take our reading of the diameter of this cylinder. So first, we place the cylinder between the anvil and the spindle. Then we turn the ratchet until we get like 3 clicks to maintain consistency. Then we use this lock to lock down our object. Then we take our reading on the main scale. So we take the last reading on the main scale that touches the edge of the thimble. That is this one here. So if you can see, we have 10, we have 11, we have 12. Then we also need to consider the half scale at the bottom. So this is 10 again, 11, 12, and 12.5. So given that, we can say that our main scale reading, NSR is equals to 12.5 millimeter. So we want to get our vernier scale reading. Which is VSR, is going to be the position that aligns with the datum line, which is this horizontal line, with the division on the vernier scale. So we can take a look at it again and see. So we have 5, 6, 5, 6, 7, 8. So we have the 8th position line, the 8th division multiplied by the least count, which is 0.01 millimeter, will give us 0.08 millimeter. So our final reading before the 0 mark offset, our final reading is equals to our main scale reading plus our vernier scale reading minus the 0 error. So this will give us 12.5 millimeter plus 0.08 millimeter, then minus the error we obtained, which is 0.25 millimeter. So this will give us, if you had 12.55 millimeter plus 0.08 millimeter, then you take away the 0 error, you are going to obtain 12.33 millimeter as your final reading. Finally, we have the vernier microscope, or sometimes we call it traveling microscope. The instrument is used for measuring tiny dimensions and has a higher precision than the micrometer screw gauge and the vernier caliper that we discussed earlier. Looking at the instrument, we have two scales. We have the main scale and the vernier scales that moves on the main scale. We also have it along this side. We also have it along this side also. This is the main scale along this vertical line here. This is the main scale, and on top of it we have the vernier scale. Then we have a knob that allows us to move forward and backward depending on the dimension and shape of the object that we want to measure. Then we can also move along the horizontal line by moving this knob from left to right or left to right, like so. Then also we can also have, here also we have another main scale reading along this line, and we have its corresponding vernier scale. These are magnifying lens that allows us to easily pick our reading on the scales. Now in our task, we want to measure the distance between these lines. So if we call this one line A1 or R1, we will also want to measure the corresponding side, which is R2. How do we do that? In order for us to do that, we need to place this plank under the microscope and find the position on the microscope where the cross wire is directly on the line. And once we find the spot, we are going to take our measurements, then move to the other line, hence traveling to the other side. And we take our measurements. The difference between those 2 points gives our final reading, or the diameter of what we want to measure. But before we take our measurements, let's learn how to pick readings on the instrument. As you can see on the main scale, We have numbers between 0 and 22. Our task is to find the smallest division on the main scale and to also find the number of divisions on the vernier scale in order for us to obtain the least count. So if you take a close look at the main scale, you will notice that we have 20 scales or 20 markings to give 1 centimeter. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is going to be the half marking. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if 20 markings give 1 centimeter, the question now is that what is 1 marking? So when you divide 1 divided by 20, it will give us 0.05 centimeter. So it therefore means that our least count, represented as LC, is equals to the smallest division on the main scale divided by the number of divisions on the vernier, giving 0.05 centimeter divided by the number of division on the main scale, on the vernier scale. So let's look at the number of divisions on the vernier scale. So now let's look at the number of division on the vernier scale. Our interest is to count how many divisions on the vernier scale. So if you count with me, you will see that this is 0, this is 1, this is 2, this is 3, this is 4, and this is 5. Making 10 marking represents 1 marking here. So 20 markings is 2.3 like that. So it means that altogether this scale here is 50. So if we then divide 0.05 centimeter, which is the smallest division on the main scale, by the number of division on the vernier, which is 50, we are going to get 0.001 centimeter. We can confirm our calculation on the instrument itself. When you look at the instrument, what you have here is we have 0.01 millimeter. So if you look at the instrument, so if your least count is 0.001 centimeter, it is the same as 0.01 millimeter as written on the instrument itself as 0.01 millimeter. Now that we know our least count, we want to get our NSR and we want to get our VSR. But in this case, we need to find the reading on one side of the line to represent our main scale reading for the first side and the vernier scale reading for this same side, and we'll get the final reading. So that means we have 2 sides. So we are going to also have the main scale reading of the second side. If this is going to be 2, this is going to be 1, and this is going to be 1. Then we also have the corresponding vernier scale reading 2 and the final reading of the second line. Then we are now going to the final reading for the whole measurement will now be the difference between these two. How do we go about that? So we are going to first place the object we want to measure under this apparatus, then I'm going to turn it based on for my convenience. I'm going to try and locate the right line via the eyepiece of the micrometer of the vernier microscope directly under the crosswire, such that the crosswire is directly on the line, on the right line. So now we can take our reading on the main scale by looking at the zero marking on the main scale and immediately taking our main scale value on the left of the zero mark of the vernier scale. So what do I mean by that? If we use our magnifying lens to pick our readings, so first thing I'm going to look at the zero mark on the vernier scale. Then I'm going to then trace it down to the main scale and pick the reading on the left of the zero marking on the vernier scale. A closer look at it, you find out that it is on the 10 marking, which is going to be 0.5. That is 10 multiplied by 0.05 will give us 0.5. So our main scale reading is on the 10 marking, and we said one division is 0.05. So this will give us 0.5 centimeter. The next is for us to consider the coincident points, which is the point that perfectly aligns with the marking on the main scale. So when you consider all these 50 markings on the vernier scale, you want to find the position of that particular vernier scale marking that best perfectly align with that on the main scale. You notice that the 14th line on the vernier scale is perfectly aligned with that on the main scale. The 14th position, we are going to multiply it by the least count. Our least count is 0.001 centimeter. Don't forget that on the instrument we have 0.01 millimeter, but because we don't want to have a different scale, so we chose to use centimeter. So if we multiply 14 by 0.001 centimeter, which is our least count, we are going to get 0.014 centimeter. Now our final reading for the first line is now going to be the sum of the main scale reading, which is 0.5 centimeter, plus our vernier scale reading, which is 0.0114 centimeter. 0.5 centimeter plus 0.014 will give us 0.514 centimeter. This is not the final reading, but this is the final reading for the first line on the plank we are measuring. Now that we are done measuring the right line of the plank, we are going to move the microscope to the left in order to pick our main scale and vernier scale reading. This we need to do by moving to the other end of the line like so. Please ensure that the plank is not moved throughout your measurement. To pick our reading, now we want to pick our main scale reading, so we can quickly use this magnifying lens to pick that. And if I count this line from 0, I'm seeing that the line is on this is 0, this is 20, this is 25. So I'm seeing that the line is around the 38 marking from 0. So if I get 38 marking, is going to be So it's going to be, so the 38 marking is going to be 38 times 0.05 centimeter will give us, so that is 1.9 centimeter. So we'll take our vernier scale reading. We can pick our vernier scale reading to look at the line coinciding with the main scale reading. So look at all the 50 lines and look at the position that best align with this. So please ensure that you use the magnifying lens in order to get the exact point as much as you can. So we can see that the 15 line best coincide with the main scale reading. So we are going to multiply the position number, which is 15, multiplied by the least count, which is 0.001 centimeter, and this will give us 0.015 centimeter. So our final reading is now going to be the addition of our main scale reading, which is 1.97 plus 0.015, which is equals to, so this goes to 1.915 centimeter. Now, in order to get the distance between these 2 points is picked at 0.514 centimeter, and the second point, which is A2, is picked at 1.915 centimeter. So the difference will give us the distance between these 2 points, which is going to be 1 point. So the distance now is equals to 1.915 centimeter minus 0.514 centimeter to give us 1.401 centimeter. So a recap of what we did, we first take the smallest division on the main scale, that is 20 points give us 1 centimeter. So 20 division gives 1 centimeter, and that is how we got 0.05 centimeter to represent the smallest division on the main scale. So this value is 1 marking on the main scale. We use that to calculate our least count by looking at the division, by dividing the smallest division, which is 0.05, by the number of division of the vernier scale, which is 50, to give us 0.01 centimeter. Then on the vernier scale, we look at the first line and we take our measurements. Our measurement on the main scale was on the 10th division, and since one scale is 0.05, and that gives us 0.5 centimeter. Then our vernier scale reading is 14 division times the least count, which is 0.001 centimeter, to give us 0.14. The addition of this gives us the position of the first line. Then we do the same on the other line by observing the reading on the main scale, which is on the 38th position on the main scale. Then we multiply it by what each division on the main scale represents, which is 0.05, to give us 1.9 centimeter. Then we also obtain the vernier scale reading for the second line, which is a line that coincides on the vernier scale with the main scale, which is on the position 15, multiplied by the least count, which is 0.01 centimeter, to arrive at 0.15. The addition of this gives us the position of the second line, which is 1.915 centimeter. The difference between this position gives us the distance between these two lines to arrive at 1.401 centimeter. Your task now is to read the manual, follow the instruction that is given, and ensure you document your experiment. Ensure you note down the necessary precaution while doing the experiment, and carry out all the exercises as indicated in the manual. Thank you all.